In this video, we discuss our first learning outcome for lesson 6.4, which is all about the central limit theorem. At the end of this video, my goal is that you would be able to state the central limit theorem in your own words. I want you to be able to describe what the central limit theorem says and what it doesn't say, as we'll talk about in the next few slides. So here is the central limit theorem as stated in our textbook. It says, for all samples of the same size n, where n is greater than 30, the sampling distribution of the sample means, x bar, may be approximated by a normal distribution, with a mean, that's a mean of the sample means, equal to the population mean, and the standard deviation of the sample means equal to the population standard deviation divided by the square root of that sample size. And this is where mu and sigma are the mean and standard deviation of the population that the sample was selected from. This is regardless of the nature of the original distribution. The original distribution could be uniform, skewed, it doesn't matter. If you know what the mean and standard deviation is of that original population, it turns out the central limit theorem says that the sampling distribution of the sample means is approximately normal when n is greater than 30. And it has this mean and standard deviation that are closely related to the mean and standard deviation of the population that the sample was selected from. So just as a reminder, we talked about sampling distributions of sample means in lesson 6.3. And I just wanted to remind you what that means exactly. The sampling distribution of sample means is a distribution of all values of the sample mean when all possible samples of the same size n are taken from the population. So maybe n is 100 and we've got a population. So we select 100 values from the population and we're selecting with replacement. And then we compute the sample mean. And then we look at the next possible sample of size n equals 100 and we compute the sample mean. And we do this for all possible samples of that size n. And then we look at the distributions or the distribution of all the values of the sample mean x bar. So here's some notation and terminology. This is the mean of the sampling distribution, or if you prefer, you can say that this is the mean of the sample means. It's denoted by this mu for mean, and then the subscript x bar says this is the mean of the sample means. And then we're saying that it's equal to the population mean of the population that data was originally selected from. And it turns out that the standard deviation of this sampling distribution is denoted this way. We have sigma sub x bar, so that's the standard deviation of the sample means, and that's equal to the standard deviation of the original population divided by the square root of the sample size. This standard deviation of the sampling distribution, or standard deviation of the sample means, is sometimes denoted by SEM and called the standard error of the mean. So you should know that. So let me give you a concrete example. So this example deals with the weights of adult males versus sample means of random samples of adult males. This is just giving you an example of a normal distribution of sample means. So let's say that the mean weight of adult males is 189 pounds, and the standard deviation for adult males is 39 pounds, and we're told that the weights of adult males are normally distributed. When we put those two pieces together, we might have a graph that looks like this. If we're looking for the probability that a particular adult male has a weight that is greater than 148 pounds, that probability would be this area over here, the area to the right of that x equals 148. And we could find that area by converting that x value to a z-score, finding out how many standard deviations that is below the mean, and then looking up the area to the right. Now we might have to look up the area to the left and infer the area to the right, but we can do that using the methods that we've discussed in lesson 6.2. Now, if we're talking about a sample of adult males, and then we're looking at the mean of that sample of adult males. We can think of the mean itself as a new continuous random variable. It turns out that since, or whenever the sample size is greater than 30, or whenever the original sample, or excuse me, the original population was normally distributed, the mean of the sample means is equal to the mean of the original population. So if the original population had a mean of 189 pounds, the sample means will have a mean of 189 pounds. Now, if you look at the standard deviation, it's a little different. The standard deviation of the sample means is the population standard deviation of those weights of adult males divided by the sample size. If we're looking at a sample size of 27 men and we're looking at the mean weight of 27 men, it turns out that that standard deviation of the sample means, or the standard error of the mean, is about 7.51 pounds. And this is what the graph looks like. Now here, if you look at a sample mean of 148 pounds, it looks like having a sample mean that's greater than 148 pounds is very likely, because having a sample mean that's less than 148 pounds is so small that I can't even see it on the graph. It seems to be very unlikely. Now over here, when we're talking about an individual male, the probability that he weighs more than 148 pounds is large, but it's not as nearly as close to 1 as it would be if we were looking at the probability that the mean weight of 27 adult males is greater than 148. Notice that this distribution on the right is tall and skinny, and this distribution on the left looks more like a traditional normal distribution. Excuse me. They're both normal distributions. This one just has a smaller standard deviation. So this is what this is saying is, with the original sample, that measure of the variation in the sample that we call the standard deviation is 39 pounds. So that is going to tell us, remember, like what percentage of people fall within 1 standard deviation of the mean, or 2 standard deviations of the mean, and so on. That standard deviation just tells us how much this graph is spread out. But when we take samples of 27 adult males, and then we compute the mean of their weights, because we're averaging those weights. I know Mr. Triola wouldn't like me using the word average, but I'm going to use the word average. Because we're averaging those together, those averages are going to tend to vary less than the original weights themselves, because you're basically taking all your outliers and then you're adding them to the other weights that are more typical, and then you add them together and you divide by the sample size. So those averages, those means, those sample means, are going to have a lot less variation than the original sample. And that is expressed by this formula right here. So if the original sample has a standard deviation of 39 pounds, it turns out that the means have a standard deviation that is equal to the original population standard deviation divided by the square root of n. Now, n is the sample size. So what that tells you is that as the sample size gets larger, that standard deviation gets smaller. And if the standard deviation gets smaller, that means your graph gets taller and skinnier, basically. We still have an area of 1 under this curve and an area of 1 under this curve. And we're talking about the whole curve, not just the green region that's been graphed here for us. But the range of values for which, let's say, like the middle 68% of the population would lie is going to be much smaller over here than it is over here. So we're going to have a much smaller variation in these sample means than we have in the original population. And when I say much smaller, I mean it's different by a factor of 1 over the square root of n, where n is the sample size. So as the sample size gets larger, this standard deviation gets smaller, which means that that graph gets skinnier. gets tall and skinny like this. Okay. So you see the weights of the adult males are distributed this way, but then when you start taking averages of those weights, when you start computing arithmetic means of those weights, then you get a distribution, that looks something like this. Now they both have the same mean of 189 pounds. This one, the mean weights of men, when you're talking about samples of 27 men, just very less whenever you're averaging those 27 weights. Okay, now in this slide we talk about a couple of things that the central limit theorem does not say. So I'm just wanting to point out some common misconceptions to you. The central limit theorem, does not say that the distribution of sample data will approach a normal distribution as the sample size increases. What the central limit theorem says is that the sample means, the distribution of the sample means, approach a normal distribution as the sample size increases. So even if the original data set is skewed, or maybe it's uniform or it has some other shape, but it's not a normal distribution. What's fascinating is that even if that original population does not have a normal distribution, if you take means from values in that sample, so you just add all of those guys together and divide by the sample size, and you do that over and over and over again. And then you look at all the sample means and then you graph them. You graph the distribution of those means. So maybe you look at a frequency distribution of each of the sample means that were calculated. It turns out that even if the original population had a skewed distribution or a uniform distribution, so maybe it's all, the graph is skewed far to the right, so it has a long right tail. When you look at the sample means, it actually has that symmetric look that we're so used to with normal distributions. Frequencies start low and then they're high and then they're low. There's symmetry about that middle line, and that middle line is where the mean is, the mean of the sample means in this case. So the sample means will approach a normal distribution as the sample size increases, again, regardless of what the original population that those data values were selected from looks like. So again, the central limit theorem does not say that the distribution of sample data approaches a normal distribution as the sample size increases. What it does say is that the distribution of sample means approaches a normal distribution as the sample size increases. So make sure you're clear that this idea of approaching normality only applies to the sample means. When it applies to some other sample statistics as well, as we talked about in lesson 6.3, but it does not apply to the sample data. So again, the central limit theorem says that sample means approach a normal distribution as sample size increases, and the mean and standard deviation of the sample means are related to the mean and standard deviation of the original population in a very specific way. The mean of the sample means is equal to the mean of the original population, and the standard deviation of the sample means is equal to the original population's standard deviation divided by the square root of n. Now, we can compute the mean and standard deviation of a population even if that population is not normally distributed. So we can still use those, we can still compute those statistics and then use those statistics to come up with the mean and standard deviation of the sample means. And it turns out that if n is large enough, we can say that sample means are, the distribution of sample means is approximated well by a normal distribution with the mean and standard deviation that we've just discussed. So that is our summary of what the central limit theorem says and what it does not say. I will see you in the next video to discuss how we apply this central limit theorem in application problems.